Alright. So, now let us look at another important aspect in understanding the mechanism of fatigue failure. So, how actually a component fail when it is under fatigue loading, right. So, the fatigue failure in general can be classified into 3 stages. The first stage is what we call crack initiation stage, followed by crack propagation stage, and followed by sudden fracture. So, first you have to have an initiation of the crack, and once that initiated crack becomes it needs to become a critical crack, right. Only when it becomes critical crack, that means a crack of critical length, only then there is going to be a fracture, sudden fracture of the component. Until then the component is safe because the crack is not yet critical. So, from the initiation stage to the stage where it becomes critical, the crack needs to change its length. That means there is a crack propagation stage, right, during which time the material is actually under surface. And once the crack reaches its critical length or the crack becomes critical, that is when the sudden failure of the component happens. So, these are the 3 stages that one would see in the case of a fatigue failure. So, if you would look at a fatigue failure specimen here, I have only shown you a schematic, but you can actually look into the textbook of Norman E. Dowling or Robert L. Norton, where there you can see the micrographs of the components which failed under fatigue, which show similar features as I have shown here. So, let us say here you have a crack initiation, this is the region you have crack initiation, and then once you have a crack initiation, that is basically your first stage, which is very short duration, because you may have a stress riser, even within very few number of cycles the stress riser or the region the feature that is responsible for rise of stress or a due to the stress concentration might actually initiate a crack, right. So, crack initiates due to stress risers such as notches, keyholes and so on, and it is extremely important to pay attention to them, even for ductile materials, because in the case of ductile materials what might happen is the material actually may because of the stress riser it may actually get into plastic deformation. So, it may yield locally, and that might actually cause the initiation of the small crack. Okay. So, the small crack gets initiated and then you have crack propagation. So, these lines that you see here, these are typically called, when you see under microscope you will see something like this, these are called beach line marks. Why they are called beach line marks? If you would go to a beach and you know that the water comes and goes back, and as a result you would on the sand surface you will see these lines kind of a thing. So, they are called, because these lines are looking similar to the beach line sand marks, they are called beach line marks, and this is a typical feature of a fatigue failure. So, you have a small crack initiation, from there you will see these lines, they are actually representing the propagation, that is what is your propagation stage. So, that is the second stage that involves most of the life of the part, because from here up to here your crack is propagating, because this is the length that is actually critical length for this component, let us say this is critical. Up to here the crack may propagate, but the component is safe, right. So, this is your most of the time is spent in this stage, crack propagation stage, and we know that the tensile stresses open the crack and compressive stresses close the crack, and that is the reason why when we are looking at different types of loading we are primarily focusing on the tensile regime, because that is where the crack propagates. But if you have a compressive regime, it is actually good for inhibiting fatigue crack propagation. Okay. And usually in this regime, the propagation regime, the growth rates are typically in the order of 10 power minus 8 to 10 power minus 4 inch per cycle. So, that means it will take several cycles for a crack to grow to a critical length. Half an inch if it has to grow, it is going to take significantly large number of cycles. And once the crack becomes critical, then there is no going back, it suddenly jips through, as we have studied in the case of our module in fracture mechanics, and then you will see the fracture surface to be relatively smooth fracture surface. That means until now you have these beach line marks and suddenly you do not see the beach line marks. If you see a failed component and if you see features like that, so there is a point from which these beach lines are coming, that means that is your crack initiation site, and then after certain distance these lines disappear and suddenly you will have a surface, a dimpled surface. That actually gives you an indication that it is actually failed in fatigue, because all these 3 stages would have passed through before the component completely failed. Okay. So, the final stage is sort of instantaneous. Once the crack becomes a critical crack, it's almost failing instantaneously. That is why you should ensure that you never reach this position when your component is in service. Okay. All right. So, now, okay, so these are the this is the mechanism of failure. This is the fatigue failure mechanism that was proposed, and we have also seen at what are the different types of dynamic loads. Okay. Now, let us say your component is subjected to repeated loading, so many cycles of loading, right. Now, depending upon the nature of loading and depending upon the number of cycles that it takes for the material to fail, there are different approaches that can be used in order to assess their fatigue response. So, if you have a material, in order to assess the material's fatigue response or fatigue behavior, there are primarily we are going to deal with 2 different approaches. One is called low cycle fatigue and another one is high cycle fatigue. So, what do we mean by low cycle fatigue? Low cycle fatigue, from the name, it implies that the component actually fails by operating at a higher stress amplitudes, but lower number of cycles. That means, it will actually fail in fewer number of cycles. The number of cycles that the component is going to be serving us will be low, and that is why it is called low cycle fatigue. And if the number of cycles that the component is giving you life is large, then that such a fatigue is called high cycle fatigue loading, okay, high cycle fatigue scenario. But what do we mean by low and high? It is always a relative term, right. So, how do we distinguish how many cycles is the boundary that I can mark below which it is low cycle fatigue and above which it is high cycle fatigue? It is very difficult to draw this sharp boundary. However, for convention, people have chosen about 1000 cycles as a reasonable thumb rule to distinguish between low cycle fatigue and high cycle fatigue. That means, if a component is designed to last for less than or equal to 1000 cycles, then you can say that the component is designed for low cycle fatigue. If the component is designed to last for more than 10 power 3 cycles or 1000 cycles, then you can say that the component is designed for high cycle fatigue. And please note that this 10 power 3 is not really a very sharp boundary. For certain materials, it can be some plus or minus 100 or 1000 cycles. It is not necessarily exactly 10 power 3 cycles, but in this class, for the sake of uniformity, what we will do is we will assume 10 power 3 cycles as the boundary. But for different materials, there are guidelines in the literature where you can actually look at the design principles, and then you will see that what are the number that is suggested as the boundary between low cycle fatigue and high cycle fatigue. Sometimes it is not a sharp boundary, you have a diffuse boundary. That means they will say that you can say that up to 10 power 5000 cycles it may be low cycle fatigue, 1000 to 5000 cycles, and say 5000 to cycles higher than 5000 it can be said as high cycle fatigue, and so on. All right. So, now, we have discussed what are the things that we have discussed. We have discussed what are the different types of loading scenarios, that is fully reversed loading, repeated loading, fluctuating loading, that is the nature of the load, right. And then we have discussed something called high cycle fatigue and low cycle fatigue, meaning the design philosophy that you would use in order to design a component which is expected to give a life of less than 1000 cycles is low cycle fatigue, and the component that is going to give a life beyond 1000 cycles, then such a component is is known to be or is considered to be subjected to high cycle fatigue. Okay, fine. So now, in order to understand or in order to design these components, what are the models that we need to use, right? What kind of a failure model that one needs to adopt in order to design components based on the different kinds of loading, right? So here we are going to talk about 3 approaches. The first one is called stress life approach, strain life approach, and linear elastic fracture mechanics approach or LEFM approach. So we are going to talk about these 3 approaches here, and in this class we will pay attention or we will study in detail the stress life approach and linear LEFM approach, and we will not study the strain life approach. Okay. So what do we mean by this stress life approach? The stress life approach is actually the oldest approach, because this is SN diagram is actually from the stress life approach, and this is usually often used for high cycle fatigue. That means if your component design, if your component is to last beyond 1000 cycles, that is when you use stress life approach. Okay? And the reason it is mostly suitable when the stresses and strain are within the elastic regime, and as a consequence it is not suitable for low cycle fatigue. The stress life approach is not suitable for low cycle fatigue. Why? If you look at your SN diagram, so let us say this is our 10 power 3 cycles and this is our 10 power 6 cycles, okay? And you see that your life is, in the case of LCF, this is your low cycle fatigue regime and this is your HCF, high cycle fatigue regime, because this is your 10 power 3 cycles, correct? Now, in this regime, your stress amplitude is usually very close to your ultimate strength. That means the magnitude of the stress that is experienced by components under low cycle fatigue regime are usually very high, and as a result there is a higher probability for these components to experience plastic deformation, right? And hence this stress life approach is not suitable, because the stress life approach assumes elastic deformations or stresses being elastic when we are doing the analysis, and hence stress life approach is not suitable for LCF, that means low cycle fatigue. And in this stress life approach we try to find out the fatigue strength or endurance limit. For the materials that have endurance limit, we will say endurance limit, otherwise it is called, in general the name is fatigue strength. That means if you take a material and if the load applied is this much, then this is the failure. So that is your fatigue strength. At this number of cycles the fatigue strength of the material is this much, and if these number of cycles the fatigue strength of the material is this much, right, and so on. And the next approach, so and then one important issue here with the stress life approach is that it cannot distinguish between initiation and propagation stages. Okay, it is mainly because everything is elastic in nature here, we are not really focusing on initiation stage, mainly we will be spending time on propagation stage, because it is extremely difficult to distinguish these 2 stages. And then we will talk about strain life approach, which is perfectly suitable for LCF, because you are dealing with strain. You can explicitly figure out what is my plastic strain induced in the material. Based on the plastic strain we will be able to do the analysis, and hence it is very much well suited for low cycle fatigue, because you can incorporate the plastic deformation into your model. It gives a very good picture of crack initiation stage, and as a result, because we are saying we are dealing with strain, then this model is particularly nicely suitable when you have significant plastic deformation or plastic strains in the material. Because you are bringing in plastic deformation as well, of the 3 approaches that we are going to discuss, that we are discussing here, this is the most complicated of all the 3, that compared to SN approach and LEFM approach. Strain life approach is a little bit more complicated. And the last one is linear elastic fracture mechanics, and this is suitable for remaining life prediction. So, if you have a crack and you know what is the cyclic loading, and then can you predict how many cycles of life is still remaining. So, that means how many more number of cycles can I run this component for before actually replacing. This is a very important information for engineers particularly, right. So, when you are having a component with a known crack size to begin with, and then you as soon as you see a crack, you are not immediately required to change the component, provided you know the information that how many cycles can I run this component before this crack becomes critical crack, and that is something that is provided by LEFM approach. So, the best model for crack propagation stage. And you know that the stress state is changing as a function of time, that means the stress is cycling between two values. And when you are talking about linear elastic fracture mechanics in the previous module, we have introduced something very important concept called stress intensity factor. K1, right. But here then when we are talking about that, then we had a static loading. But now you have a cyclic loading, and hence now when we are doing this LEFM approach for crack propagation under dynamic loading, you have to deal with something called cyclic stress intensity factor. That is the crack driver, right. Because when the stress intensity factor in the fracture mechanics, we have learned that when K1 is equal to K1C, that is when failure happens, that means crack propagates. Here what we need to look at is something called cyclic stress intensity factor, because your stress is cycling between two stress states. Okay. So, here we have the summary of this discussion is we have three fatigue failure models, and of the three, the first one is stress life approach, second one is strain life approach, and the third one is LEFM approach. Okay. And in this class we are only going to discuss about stress life approach and LEFM approach, and we are not going to discuss strain life approach. Okay. And we will spend most of our time on stress life approach. Okay. So, we have discussed this stress life approach and strain life approach, and we said that stress life approach is best suited for HCF, high cycle fatigue regime, and strain life approach is best suited for low cycle fatigue regime, right, fine. But what are the different components, engineering components, that actually needs to be designed for one of these scenarios, whether I need to design a component for high cycle fatigue or low cycle fatigue. So, some examples, for instance, if you take an automobile crankshaft, you would expect your automobile crankshaft to last for several years, right. That means you do not want to change it every 1000 cycles or 10,000 cycles. You really want it to last for few 100 million cycles, and ideally you do not want your crankshaft to break down at all even before you discard your car, right. That is the kind of expectation that you have. That means you are expecting extremely large number of cycles of life for this crankshaft. Since you are expecting extremely large number of cycles, you have to ensure that the stress amplitude that you are applying on this component is relatively low, and as a result this automobile crankshaft qualifies to be a component that is designed for high cycle fatigue, right. Typically the number of cycles that you would expect is about 200 million cycles typically for a crankshaft, and that is why it is designed as a high cycle fatigue component. On the other hand, you have certain other critical components like aircraft bodies, ship hulls, and so on. They are having so many cycles of known stress, but sometimes these components are subjected to unknown stresses of large magnitude. For instance, if you are flying, if there is an aircraft, then it is highly possible that it may encounter a turbulence during the flight. Same is the case with ships, right. They may be experiencing severe storms while sailing, and these are the stress levels which are not usually within the operating stress levels of these components, and hence they might actually exceed these loads that are coming onto the structures might actually exceed the design loads, which might cause local yielding. And hence you should not design these guys for high cycle fatigue. You should design them for usually low cycle fatigue, and then usually they are for the design of these components we use strain life approach together with LEFM or the fracture mechanics approach, strain life approach together with fracture mechanics approach in order to design the components such as aircraft bodies, ship hulls or nuclear reactor components and so on, which are critical and known to be subjected to very high stress levels. All right. So, before we move on, this is a very important slide where we need to understand the definition of various parameters when we are talking about a fatigue loading. Here we are showing a fluctuating loading scenario. So, this is a most general loading scenario wherein you have a minimum stress to be negative, you can see this is 0 and maximum stress to be positive. That is what I said, a fluctuating loading scenario can actually have some part in tensile regime, some part in compressive regime. Okay. And then I should have drawn this with, so let me put that in, okay. Let me draw that in green color, and that green color one is our mean stress. Okay. All right. So, this is the way that is loading, and now we define 5 important parameters. The first one is called cyclic stress range. That is basically the difference between the maximum stress and minimum stress. That is actually the distance between the peak and the valley, and designated as delta sigma. And this is what we call cyclic stress range, that is sigma max minus sigma min, the maximum stress minus minimum stress. Then very important quantity called stress amplitude. What is stress amplitude? Stress amplitude is actually the distance between the mean stress to the maximum stress or mean stress to the minimum stress, because the mean stress is supposed to be halfway through maximum and minimum. That is why sigma max minus sigma min by 2. And this is what is important, stress amplitude. And when we have drawn SN diagram, on the y axis what we have drawn is the stress amplitude. That S in SN diagram is actually the stress amplitude. Okay. And the mean stress is actually sigma max plus sigma min by 2, and when sigma max equal to negative of sigma min, that is for fully reversible loading, then it will become 0, otherwise it will be non-zero. Depending upon the magnitude of sigma min compared to sigma max, this mean stress could be positive or negative. If your sigma min magnitude is larger than sigma max magnitude, then the mean stress would be negative, otherwise it will be positive. If both of them are equal, then it becomes 0. That is about our mean stress. And then we have something called stress ratio. Stress ratio R is defined as minimum stress to maximum stress. The numerator is minimum stress, denominator is maximum stress. Okay. And then we also define something called amplitude ratio, that is ratio of the stress amplitude to the mean stress. Okay. So, by looking at these two guys, you can actually say which kind of a loading the material is subjected to. What is the nature of loading, whether it is fully reversible loading or a fluctuating loading or a repeated loading, by looking at this guy, right. So, let us look at the case of a fully reversible loading. So, for the fully reversible loading, sigma min, so fully reversible loading is sigma max is equal to negative of sigma min or vice versa. What is R? R is sigma min by sigma max. So, R is equal to minus, sigma min by sigma max. So, that is minus 1, because sigma max is equal to negative of sigma min. So, when R is equal to stress ratio is minus 1, then it is fully reversible loading. And what happens to the amplitude? Amplitude is sigma A by sigma m. We know that mean stress in the case of fully reversible loading is 0, that means it becomes infinity. For a repeated loading, we know that minimum stress is 0, right. Since it is 0, the minimum stress is 0, R becomes 0, and sigma stress amplitude and mean stress are the same for repeated loading, and hence amplitude is equal to 1. So, by looking at the stress ratio and amplitude ratio, you can actually say, you can actually find out the nature of the loading for the given problem. Okay. So, these are very important to understand and remember as well.